Hi everyone, and welcome to this short introduction of our paper, Bridging Future Learning and Adaptation, New Challenges of Support Query Shift. In this work, we introduce a new and challenging problem, which wasn't defined in the literature until now. We call it Future Learning under Support Query Shift. First thing first, let's introduce Future Learning with a real-life use case I used to work on. I am an online hardware store, and I want to add to my website a visual recommendation feature so that my customers can upload a photograph of one of their tools and see a recommendation of similar tools. So given this picture of a drill, I want my model to predict whether it's a saw, a mower, or a drill. The most intuitive solution here is to just load a model pre-trained on ImageNet and fine-tune it on a few dozens of labeled pictures of saws, mowers, and drills. Boom, problem solved, I get around 90% accuracy. But in reality, you hardly ever have dozens of labeled pictures at your disposal. This hardware store, for instance, only has a small catalog. For each product, it might have only 3, 2, or even 1 sample. With that few examples, the model won't be able to effectively fine-tune and learn features specific to saws, mowers, and drills. Thus a huge drop in accuracy. This problem is called future learning, and it's attracting a lot of attention in the community with about 1,000 articles in 2020. We formulate this problem like this. Given a support set of labeled instances, typically 1 to 5 per class, a query set of instances to classify among the same classes, and a base set constituted of labeled images that belong to other classes, you want to maximize your accuracy on the query set. And the most common approach in the literature is to train a feature extractor on the base set in such a way that representations are as general as possible, as opposed to representations specific to the classes of the base set. Then at inference time, we just process both support and query images through this feature extractor and classify query images based on their distance to support images in the feature space. An intuitive way to do so, which is called Prototypical Networks, is to use the mean of the feature vectors for each class, which we'll call the prototype of this class, and then just classify each query as the closest prototype with respect to Euclidean distance. Methods that build on this idea are getting pretty good at future learning, and are now exceeding 90% accuracy on 5-shot third ImageNet, which is a popular benchmark. However, you can see that in this example I showed you, all images come in the exact same context. They're all catalog images on a clean white background. It's a relevant assumption for the support set because the pictures in the store's catalog are like this. But for a query set, it's an unrealistic assumption because when the customer uploads a picture of their tool at home, it will look a lot more like this. In this setting, if we just naively apply prototypical networks, support and query instances will likely be cast into completely different regions of the feature space, and we'll be unable to classify them with a simple comparison. In the literature, when training and test images are drawn from distinct distributions, we call this distribution shift or domain shift. When we have a lot of data in both domains, a well-known solution is to train a model to align the two distributions. But in this case, it's much more complicated because we don't have thousands of images to train a model to align the two distributions. We only have a dozen of images in the support domain and another dozen in the query domain. This is a novel and yet untitled problem. This is future learning under support query shift, or FSQS for short. It's not an easy problem to solve, and we kind of figured that we wouldn't be able to solve it immediately. First, we wanted to give the community everything we need to get better on this problem. So to be a bit more specific, we built FuShiftPed, which is a benchmark with 3 datasets specifically designed for FSQS. We provided the same code base to allow anyone to easily learn their own reproducible experiments. And we developed a strong baseline combining the best of future learning and domain adaptation. The first question we asked ourselves was, how can we evaluate the method on the FSQS problem? In classical future learning, what we do is we split all classes that we have between base and test set. The model is allowed to train on the base set. Then to evaluate it, we randomly generate lots and lots of future tasks from the test set and aggregate the results. To generate a task, typically we sample a few classes at random, then we sample a few images of these classes to put in the support set, and some others to put in the query set. This way we're sure to evaluate the model's ability to discover new classes from a few examples. In FSQS, there is another subtlety, since we want to generalize not only to new classes, but also to new domains. So we want a dataset with a lot of classes, but also a lot of distinct domains. Then we split both classes and domains between base and test set. The model is allowed to train on the base set, and then we sample a lot of FSQS tasks from the test set and aggregate the results. Here, to generate a task, we sample a few classes and 2 distinct domains. We sample a few images from each class and from the first domain to constitute the support set, and some other images from the same classes, but in the second domain this time, to constitute the query set. So how can we find a dataset with that many domains? There is no such thing in the literature. Most domain adaptation benchmarks offer 3, 4, sometimes 7 domains, but it's not enough in our case, because we need several domains for both the base set, the test set, and even the validation set. We actually need dozens of domains. The solution we found was to create these domains artificially, from perturbations applied to the images. We use around 20 standard perturbations with several levels of intensity and make the assumption that images processed by one perturbation constitute a distinct domain. This gives us a lot of domains, largely enough to separate between base and test sets. We applied this method to Mini-ImageNet, which is a common future cloning benchmark, and also to Sci-Fi 100. The drawback here is that those domains are totally artificial. To complete our benchmark with organic domains, we use FemNist, which is MNIST but extended with lower and uppercase characters and augmented with the information about who wrote each character. We considered each character as a distinct class and each writer as a distinct domain. So we split among both characters and writers to build a beautiful support query shift dataset. Now that we have datasets to evaluate novel methods on the FSQS problem, we need something to compare to. So we came up with the first method dedicated to FSQS. Remember that we assume that the main issue raised in this setting is that query and support features lie in distinct regions of the feature space, so we can't classify them with a naive comparison. But if we're able to transport support features to align their distribution with that of query features, it's a win. To do this, we use optimal transport. You can think of the optimal transport from a source distribution to a target distribution as the cheapest transportation plan that would align the source distribution with the target distribution. In this example, we have two discrete distributions with the exact same number of samples. The transportation cost from a source sample to a target sample will intuitively be the Euclidean distance between the 2 points. And the optimal transport from the source to the target distribution would be the pairwise matching between the two that minimizes the sum of the cost of all pairs. Finally, in order to have a softer matching, meaning that we don't necessarily want to assign each source sample to exactly one target sample, but rather globally project a distribution on the other, we had an entropical realization on the transport. So we're going to use this method to align our support features with our query features, and that way solve the task of feature cloning under support query shift. First, we cast support and query images into the feature space with our trained feature extractor. As we said, both feature sets lie in distinct areas of the feature space, which is no trouble for us because we compute a transport plan from the support set to the query set and obtain a transported support set that is aligned with the query set. Now we just apply prototypical networks to classify queries with respect to their Euclidean distance to the transported prototypes. Thankfully, we are able to show that applying this optimal transport effectively improved the performance of prototypical networks on the FSQS problem, which is frankly not surprising since prototypical networks were not designed for this new and challenging problem. But as you can see, by comparing the second and third lines of this table, our algorithm transported prototypes still suffers from a huge performance drop in the case of support query shift, compared to the case where there is no support query shift, which corresponds to standard feature cloning. This shows that transported prototypes are just a baseline and that there is still a huge room for improvement on this problem. We've basically just laid the groundwork towards solving feature cloning under support query shift. Not only is there a big room for improvement accuracy-wise, but there are also some very important open questions about episodic training, for instance. A lot of recent works are questioning its efficiency in classical feature cloning, and our experiments show that in FSQS, depending on the setup and the dataset, episodic training will either improve or harm the performance. So we strongly encourage a deeper study on when and where episodic training can help us. And finally, you'll notice that support query shift is a transductive problem by nature, meaning that we process the query set as a whole and therefore can use the information from all queries to classify each one of them, as opposed to an inductive setting where each query is processed independently from the others. From this observation, we can ask ourselves a lot of questions like the importance of the size of the query set or the role of batch normalization, which we study in our paper. And the ultimate question, of course, would be, can we adapt to a support query shift in an inductive fashion? If I have a support set of catalog images with a clean white background, and a customer sends me a picture of their mower laying on a lawn, could I be able to successfully classify it without waiting for other images? Once we crack that, we'll win the jackpot. Thank you for your attention. I hope everything was as clear as day, and if not, you're welcome to check our paper or reach out to us by mail or any other network you see fit. Have a great day.